Okay, well, we've seen now that the prime factorization certainly is useful, and so that means we ought to start thinking about how to find that prime factorization. Basically, that prime factorization, we've already used it in some of the theorems we've proved in earlier presentations, but it certainly has quite a few applications besides those theorems. But the big question is, how do we find that prime factorization? And then, much more importantly, actually, how do we find it an acceptable time? Because we're going to see our first stab here, our trial division approach, that will give the prime factorization. It's just going to take forever. And, well, the ability to factor numbers connects to the ability to find large prime numbers, which are needed for internet security, as well as to the ability to crack internet encryptions by factoring the numbers that are used in the code. Because of these considerations, there is a lot of interest in this question: how do you find the prime factorization of a number? And so basically, for the latest on this field, it's best to check the current literature if you can access it. That doesn't necessarily mean that your library is poor, but I'm quite certain that some of that literature actually is classified and therefore will not see the light of day until some declassification date, because intelligence agencies certainly are just as interested in these kinds of factorizations as private enterprise is. In this first presentation, we're just going to start introducing a recurrent theme, because we're going to talk about factorization algorithms very much repeatedly. As I mentioned in the introduction to the course, a large part of this course could basically be considered, well, how do you check whether something is a prime number, and how do you factor certain numbers? Okay, so trial division, the elementary way to approach numbers, well, how do you factor the number 91? Well, you just try all the prime numbers, right? 2 doesn't divide 91, 3 doesn't divide 91, 5 doesn't divide 91, 7 does divide 91. So that means that 91 is 7 times x, and x is 91 divided by 7. That takes a minute. But the result is 13. In one talk, I think it was John Conway whose talk I attended, he said 91 is the first number that looks like it's a prime number, but it isn't. And that's because its factors are 7 and 13, for which division tests are a little bit harder than for the other early prime numbers. Okay, so 91 is 7 times 13, and that doesn't seem so bad until you try it with a number like this: 53,198,462,352. Good luck, because that actually shows it's quite bad, because the factorization is this number consists of these two factors here: 11,113,111 and 4,787. No, I didn't invent that number. I basically went into my computer algebra system, MathCAD, and just typed in a large number and asked for the factorization, and then messed around with it until I had an ugly factorization, right? This is one that is really hard to factor, because we don't easily, or with an elementary method, jump to 4,787 and say, yes, that is one of the factors, and now let's divide. Okay, so how can we guess the factors in a more structured fashion? That's what we talk about Fermat for factorization. Basically, if you've got an odd positive integer, and we really are only worried about odd numbers, right, because even numbers are composite by default. Well, for those numbers, there is a one-to-one correspondence between the factorization of n into two positive integers and the differences of two squares that equal n, and that goes like this. If you write a factorization of n as ab equals n equals t squared minus s squared, right? We want to have a correspondence between the factorization and the differences of two squares. Well, that would mean that you need t squared minus s squared to be a times b. And if you use t equals a plus b over 2 and s equals a minus b over 2, you can work it out for yourself with the binomial formula. That gives you that t squared minus s squared is ab. And so the one-to-one correspondence, the injective function, is that we consider the factorization itself as the input ab, and the output is f of ab being t and s. And that's a plus b over 2 and a minus b over 2. So that's not that bad. But this can be implemented as a factorization method, because what we do know now is that any factorization goes along with a difference of two squares. And so basically you could start by just taking your number t to be the smallest integer that is greater than the square root of n. And then you just look for perfect squares in the sequence t squared minus n, t plus 1 squared minus n, t plus 2 squared minus n, and so on and so on. And whenever you find a perfect square, well, then s squared equals t plus k squared minus n would give you that n is t plus k squared minus s squared, and we know that that's t plus k plus s times t plus k minus s. And because n is n plus 1 over 2 squared minus n minus 1 over 2 squared, we will ultimately find a number, and we will find that number in at most n halves minus square root of n steps, because that's how long it takes to go from square root of n to n plus 1 divided by 2. Not quite sure about the number of steps here right now, but it ought to work out. It is at least a linear number of steps, and that is really all that counts, is capital O of n. But we cannot jump directly to the end, or let's just say we can, but it wouldn't really help much, because if we're using the difference n plus 1 over 2 squared and n minus 1 over 2 squared, that just gives you the trivial factorization n equals n times 1. Okay, as examples, factoring 1363 takes one step with this method. And why is that the case? Well, I've implemented it in MathCAD, and so if I take 1363, and if I then take t to be the first integer that is above the square root of n, well, then I can compute t squared, and I can compute the numbers qk being t plus k squared minus n, and I can compute the square roots, and whenever the square root is an integer, I know I've found a perfect square here. And if we're starting with 1363, in the first step I end up with a perfect square. Okay, so that's great. If I want to factor 1463, well, I just change everything to 1463, and you can see that in 9 steps, or 10 steps if we count the zeroth one here, we end up with a perfect square. And so that is still, I mean, 10 steps is nothing. That's very quick, and the factorization is 7 times 11 times 19. Well, yeah, okay, so direct checking still would have worked pretty well. However, if you are having products of factors that are not approximately equal, this Fermat factorization can take a lot longer, because after all, we're starting with the situation that the factors are approximately equal, because we're starting around the square root of n. And so, for example, 1461 is divisible by 3, which is about as easy as it comes, right? And Fermat factorization doesn't yield a factorization in 100 steps. So 1461, well, that's 3 times 487. And, well, you can just go through this and then also continue here. And if you just scroll through, everything has a decimal point. None of the square roots actually ends up being an integer up to step 100 here. And of course, that's natural, right? Because for this number, we start somewhere around the square root, and then we count up and we count down. But we're not really getting anywhere, because the factors are very much on the outside of this spectrum, in the middle of which the square root sits. Okay. On the other hand, Fermat factorization brings up, as often is the case in number theory, the name of Fermat. And Fermat had all sorts of beautiful conjectures. And so, for example, numbers of the form 2 to the 2 to the n plus 1 are called Fermat numbers. And Fermat conjectured that all these numbers are prime numbers, and that turned out to be incorrect, in fact quite impressively so, because here's a first example. 2 to the 2 to the 5th plus 1 is equal to 641 times 6,700,417. That was observed by Euler in 1732, so way before there were computers that could do this kind of stuff. Not quite sure how Euler figured it out, but Euler was famous for being extremely good with numbers in his head, and it's I wouldn't put it past Euler to even have found the factor 641 by direct checking. The way we can work it out here with a little bit more elegance, because we already know what the result is and we don't want to just say, well, yeah, stick it in a computer and the computer tells it to you. We can notice that 641 is 5 times 2 to the 7th, and that's because, let's see, 2 to the 7th is 128 times 5 is 640 plus 1 is 641. And 641 is also 2 to the 4th plus 5 to the 4th. So 2 to the 4th is 4 squared is 16. 5 to the 4th is 25 squared is 625. And 16 plus 625 is 641. And if you then look at 2 to the 5th plus 1, well, that's 2 to the 32 plus 1, which is 2 to the 4th times 2 to the 28th plus 1, which is 641 minus 5 to the 4th from what we have up here, times 2 to the 28th plus 1, and that knocks out the 2 to the 28th, right? Because this is now 641 times 2 to the 28th minus 5 times 2 to the 7th to the 4th. And, well, 5 times 2 to the 7th is 641 minus 1, right? And everything else stayed the same. And here we realize now, as we raise that to the 4th, we end up with a minus 1 at the end, which cancels with a plus 1, and everything else has a factor 641. So this ends up being 641 times 2 to the 28th from the first one. Then we've got 641 to the 4th, which is 641 times 641 cubed and the minus sign. Then we've got 4 times 641 cubed with a minus minus, which would give us a plus. So that would be 4 times 641 squared times 641. Then we've got 6 times 641 squared with a minus, so minus 6 times 641 times 641. Then we have minus 4 times 641 with an extra minus here, so that would be plus 4 times 641. And then we end up with minus 1 to the 4th plus 1, that cancels out. And, well, so that means that 641 divides 2 to the 5th plus 1. And now you do the division, and that would do it. I would have to say here, with all honesty, that yeah, I had to look that up. I'm really not sure, but with computing devices available, certainly I would almost be willing to bet money on the fact that the days of doing these kinds of factorizations in your head are basically over, at least in terms of finding new results. It's certainly still a valuable skill to just get a feel for how the pattern works. But anything that we can do as a factorization in our heads is something that can be done with computers. And so for a lot of what we're going to do, as you have already seen in this MathCAD sheet for the Fermat factorization, we will have to use computers. Nonetheless, whenever you've got a homework problem that basically says play with the numbers, if the numbers aren't too ugly, work it out with paper and pencil just to get a feel for how the numbers work. That is certainly not something that is bad for you, but also realize that when it comes to industrial type applications, you will most definitely have to use a computer. All right, we move on here. And, well, now that we know that there is a Fermat number that is not prime, the next question is which Fermat numbers are prime? And there is a theorem that will later on be an exercise, so we're not going to prove it here. And that is every prime divisor of a Fermat number 2 to the n plus 1 is of the form 2 to the n plus 1 times k plus 1. Okay, well, if we know that, then 2 to the 3 plus 1 is prime, because 2 to the 4 to the because the only divisors would be 2 to the 4 times k plus 1, which would be 16k plus 1, and 2 to the 3, that's 2 to the 8th, which is 256, plus 1 is 257. That is not divisible by 17, which would be 16 times 1 plus 1. And all other numbers of the form 16k plus 1 are too large to be factors. In fact, 17 squared is 289, so that would be too large to be a factor already. Okay, as another example, 2 to the 6th is not prime, but it would take a while until a factor 200 is, so it's not prime, so it's not prime, but it takes a while until you find a factor, and the factor would be 256 times 1071 plus 1. Let's see, how does that go? 2 to the 2 to the 6. That would be 2 to the n plus 1, 2 to the 7th times k, and 2 to the 7th is 128, and so then you would be dealing with number times 128, and 128 is half of 256, so that's where that part came from. Yeah. Okay, so that takes a while. Some more facts about Fermat numbers. Only the first four Fermat numbers are known to be prime, and here they are. I mean, 2 to the 2 to the first plus 1, well, that's 4 plus 1, that's 5. We have 16 plus 1, that's 17. Here it's getting a little bit more complicated, because that's 257, 2 to the 8th, 256 plus 1. 2 to the 2 to the 4th, 2 to the 16th, that's a number that I remember from my Commodore 64 days, because 2 to the 16 minus 1 is 65,000, or 2 to the 16 is 65,536, minus 1 would be 65,535, and that was the number of bytes that were free on that machine, I think, on the initial screen. Maybe it's 65,536, I don't remember right now, but plus 1 gives us this one. Another 243 of these Fermat numbers are known to be composite, and after that we don't know, so certainly now there is a conjecture that all but the first 4 Fermat numbers are prime, but the research in that direction really tests the limit of what's possible, because for only 7 of the composite Fermat numbers do we have the complete factorization. That at first seems kind of strange, right? We've got 243 that are known to be composite, and for only 7 of them do we have a complete factorization. I would assume for the other ones we have at least one factor, but think about it. If we're looking at the 12th Fermat number, that would be 2 to the 2 to the 12th plus 1. Well, 2 to the 12th, that would be 2 to the 4,096, because, and the way I always cue off of that is that 2 to the 10th is 1,024, and then times 4 would be 4,000 something, so 4,000, excuse me, 4,096 in this case. And, well, if you're working that out here, I think I just took the log to base 10, and that's greater than 10 to the 1,365, so that is a number with over 1,360 digits. And even if you find a small factor, even if you find a factor with 20 digits, you're left with a number with 1,345 digits or so. That's not something that you're going to continue factoring, right? So that is why those Fermat numbers certainly give you all sorts of ideas for research. If you can factor Fermat numbers, if you find something to do that, you probably have something that can factor all sorts of other things also. Another fact about Fermat numbers is that if the kth Fermat number is 2 to the 2 to the k plus 1, then for all positive integers n, we have that the product of the 0th through the n minus 1st Fermat number is the nth Fermat number minus 2. And, well, that's an induction on n. For n equals 2, what do we get? We get f0 times f1. f0 would be 2 to the first, yeah, right, 2 to the 2 to the 0th, so that would be 2 to the first, which is 2 plus 1 is 3, and then the f1 would be 2 to the 2 plus 1, that's 5, so 3 times 5, and the f2 Fermat number is 2 to the 4th minus 1, which is 16 minus 1, which is 15, so that works because that is, okay, 3 times 5 is 15, and that's 17 minus 2, and 17 is 16 plus 1, which was the Fermat number, the second Fermat number. Goodness gracious, the counting is ugly here. Okay, so now the induction step takes the product, does what we usually do with a long product. It splits off the first n minus 1 factors, which are nth Fermat number minus 1 times fn, and now we just write it out. That's 2 to the 2 to the n minus 1 times 2 to the 2 to the n plus 1, and that's 2 to the 2 to the n plus 2 to the n minus 1, which is 2 to the 2 to the n plus 1, because that's 2 times 2 to the n here, right, which is 2 to the n plus 1, and minus 1 is plus 1 minus 2, and that's fn plus 1 minus 2, and that's already it. Okay, what else can we do? For distinct non-negative integers, the Fermat numbers fn and fm are relatively prime, and consequently that means, again, there must be infinitely many prime numbers, so this is another way to prove that there are infinitely many prime numbers, and we in fact now also have a sequence, an infinite sequence of numbers that are relatively prime here. Namely, without loss of generality, we let m smaller than n, and we suppose for a contradiction that there is a number that divides fn and fm. Well, then d divides fn, and it divides the product of the earlier numbers, because the earlier numbers contain fm, and that means, because this difference is 2, that would mean that d divides 2, and there's a contradiction right there, because those Fermat numbers are all odd numbers, and so their divisors are all odd. Okay, and so now if there were only finitely many prime numbers, say capital N of them, then 2 of f0 through fn would not be relatively prime, because each fk has a prime factor that doesn't occur in any of the factorizations of the earlier ones, and f0 is itself a prime number. Okay, a theorem that we're going to state without proof. Fermat numbers, they look really weird. They look like a play thing, but all of a sudden, here's a very deep result from geometry that talks about a regular polygon with n sides, and when it can be constructed with straight edge and compass, which is a classical problem dating all the way back to the ancient Greeks that us mathematicians are so fond of. And so this straight edge and compass construction of a regular polygon with n sides is possible if and only if n is the product of a non-negative number, non-negative power of 2, and a non-negative number of distinct Fermat prime numbers. Okay, so that means if there are huge Fermat prime numbers, then there are also huge and rather strange regular polygons with n sides, and otherwise there certainly are interesting regular polygons with huge numbers n of sides by just making the power of 2 very big. And that looks like something that is really deep. I've once gone through the proof that an angle cannot be trisected with straight edge and compass, and that sort of goes in the same direction, I think, and that proof was really, really hard, so I imagine this one would also take quite a while. So we move on, and just to finish this one out, we're going to change gears a little bit. We're going to talk about Diophantine equations, and basically an equation is a Diophantine equation if we only allow integral solutions. And so that means basically any equation you want is a Diophantine equation as long as you only allow integer solutions. And so, for example, the Diophantine equation ax plus by equals c, that asks for all points on this straight line whose coordinates are integers. And technically, we solve Diophantine equations anytime we convert currency, because you go to whole dollars or whole cents or so. Certainly rounding helps here if the equation doesn't work out, but at the same time, you also have to think about what kinds of bills people have available. So for example, if I wanted to exchange $1,000 into euros, by the time I made the slides, $1,000 bought about 710 euros. And suppose that the bank has only 20 and 50 euro bills. Well, how can the 710 euros be paid out? Well, let's see. You can go with multiples of 50 at first. The last 10 you can't get, but with 3 20s, you can pay down 60 bucks, and the remaining 650 can be paid out in 50 euro bills, right? So that works. And 715 euros, of course, cannot be paid out because 20s and 50s all end in 0, and so 715 cannot be paid out in that currency, and so then you have to work out another way to make the exchange, maybe get a couple of dollars back or so. Okay, so that's one of the interests in Diophantine equations. Every so often, even in real life, we have an interest in getting integer solutions. And so if you've got non-zero integers a, b, and c, then the equation ax plus by equals c has an integral or an integer solution xy if and only if the greatest common divisor of a and b divides c, and in this case the equation has infinitely many solutions. So we have to be careful here. On one hand, the solution of the equation is of course a doubleton, so it's correct to say xy here. This is not the greatest common divisor, this is the solution doubleton, the solution pair, whereas ab here, this really denotes the greatest common divisor of a and b. Okay, how do you work this out? Well, we go left to right, so we assume that this thing has an integer solution. Then, by an earlier result, we know that all the linear combinations of a and b are multiples of the greatest common divisor of a and b, and so that means that c must be a multiple of the greatest common divisor of a and b. Well, that wasn't too bad. And so if we go the other way, if c is divided by the greatest common divisor, so if c is a multiple z times greatest common divisor of a and b, then we can find s and t, so that s times a plus t times b is the greatest common divisor of a and b. And then we can just use x being zs and y being zt, right? Because then zsa plus ztb would be an integer solution of the equation xa plus yb equals zab, and zab is c. Regarding the infinitely many solutions, we just note that in the real numbers, the solutions are on the line ax plus by equals c, which goes through the point zs zt, as we have seen, and which has slope negative a over b, which is a rational slope, and that means all numbers of the form zs plus kb zt minus ka, that's when you hit the next integer, right? When you have a slope negative a over b, if you take k times b steps in the x direction, you take negative k times a steps in the y direction, and you hit another integer. So with k element z here, those are solutions too, and those are infinitely many. Note that we really didn't need geometry for this last part, but it really helps with the idea to just draw the picture, and I recommend you should draw that picture if it does not just simply materialize in your mind. The interesting thing here is that every so often even number theory connects to geometry, and you want to work out those pictures for yourself. If we have n non-zero integers, then the equation a1 x1 through all the way through xn a n equals c has an integer solution x1 through xn if and only if the greatest common divisor of a1 through an divides c, and in this case the equation has infinitely many solutions again. Well, that proof should be very similar. So first we note that the greatest common divisor of a1 through an is the greatest common divisor of a1 through an minus 2 and the greatest common divisor of an minus 1 and an. And that is the greatest common divisor of a1 through an minus 2 and some linear combination of an minus 1 and an. And now we can just keep doing this and end up with the fact that the greatest common divisor of a1 through an is also a linear combination of the a1 through an. And in fact, any integer of this form is a multiple of the greatest common divisor of a1 through an. That's an induction proof, which I want you to do separately. I'm not going to do that here. And then you would just mimic the proof of the previous result, which is another good exercise that I would want you to do at this stage. Personally, I'm getting tired one more time. I only recorded 2 presentations in a row here, but making these slides, actually I have to tweak some of them, because when I made them, I made some notes that said, okay, here look something up in the book again, or here do something with MathCAD. Well, I'm ready to call it a day. If you are, have a good night's sleep, or at least take a good break before you hit some of the homework problems, because you've got to practice working with these things. All right, I'll see you in the next one. Because of these considerations, there is a lot of interest in this question: how do you find the prime factorization of a number? And so basically, for the latest on this field, it's best to check the current literature if you can access it. That doesn't necessarily mean that your library is poor, but I'm quite certain that some of that literature actually is classified and therefore will not see the light of day until some declassification date, because intelligence agencies certainly are just as interested in these kinds of factorizations as private enterprise is. In this first presentation, we're just going to start introducing a recurrent theme, because we're going to talk about factorization algorithms very much repeatedly. As I mentioned in the introduction to the course, a large part of this course could basically be considered, well, how do you check whether something is a prime number, and how do you factor certain numbers? Okay, so trial division, the elementary way to approach numbers. Well, how do you factor the number 91? Well, you just try all the prime numbers, right? 2 doesn't divide 91. 3 doesn't divide 91. 5 doesn't divide 91. 7 does divide 91. So that means that 91 is 7 times x, and x is 91 divided by 7. That takes a minute. But the result is 13. In one talk, I think it was John Conway whose talk I attended, he said 91 is the first number that looks like it's a prime number, but it isn't. And that's because its factors are 7 and 13, for which division tests are a little bit harder than for the other early prime numbers. Okay, so 91 is 7 times 13, and that doesn't seem so bad until you try it with a number like this, 53,198,000,198. We talk about Fermat for factorization. Basically, if you've got an odd positive integer, and we really are only worried about odd numbers, right, because even numbers are composite by default. Well, for those numbers, there is a one-to-one correspondence between the factorization of n into two positive integers and the differences of two squares that equal n, and that goes like this. If you write a factorization of n as ab equals n equals t squared minus s squared, right, we want to have a correspondence between the factorization and the differences of two squares. Well, that would mean that you need t squared minus s squared to be a times b. And if you use t equals a plus b over 2 and s equals a minus b over 2, you can work it out for yourself with the binomial formula that gives you that t squared minus s squared is ab. And so the one-to-one correspondent, 1,462,352, good luck, because that actually shows it's quite bad, because the factorization is, this number consists of these two factors here, 11,113,111 and 4,787. No, I didn't invent that number. I basically went into my computer algebra system, MathCAD, and just typed in a large number and asked for the factorization, and then messed around with it until I had an ugly factorization, right? This is one that is really hard to factor, because we don't easily, or with an elementary method, jump to 4,787 and say, yes, that is one of the factors, and now let's divide. Okay, so how can we guess the factors in a more structured fashion? That's what we... Okay, well, we've seen now that the prime factorization certainly is useful, and so that means we ought to start thinking about how to find that prime factorization. Basically, that prime factorization, we've already used it in some of the theorems we've proved in earlier presentations, but it certainly has quite a few applications besides those theorems. But the big question is, how do we find that prime factorization? And then, much more importantly, actually, how do we find it in acceptable time? Because we're going to see our first stab here, our trial division approach, that will give the prime factorization. It's just going to take forever. And, well, the ability to factor numbers connects to the ability to find large prime numbers, which are needed for internet security, as well as to the ability to crack internet encryptions by factoring the numbers that are used in the code.